Hello, everyone, and welcome to another Emergency Stat 1793 video lecture. So I'd like to just thank you all for your patience and understanding as we sort of deal with this need to go online for a couple of these lectures. I'm hoping that by the end of reading week, we'll be back to normal, everyone back in class, back in person. But for now, I hope that these video lectures are serving well enough. And I'll just remind you that even though we're sort of dealing with lectures for this material that are sort of pre-recorded, if you have any questions about any of the material here, I would encourage you to reach out to me, set up some time to chat about things, ask me questions over emails, or set up some time once we're back in person, and I'm happy to go over anything at all with you from these lectures. So in today's lecture video, what we'll talk about is sort of the natural follow-on to what we've been dealing with in this course for the last little while, right? So in the last lecture, we were finishing up talking about expectations and variances when we have multiple random quantities. And that sort of ends off our general discussion of discrete random variables. The one thing that we haven't really talked a lot about is how do we actually go about finding the distribution functions, the probability mass function, for instance, for different discrete random variables. And we saw how we can work these out if we're using, for instance, the setup based on the sample space and calculating probabilities like we did with events sort of early on in the course. But we haven't really talked about, how do we know what the probability mass function is going to be? And so in today's lesson, what we want to see is how can we go about figuring this out? And the basic idea of what we're going to rely on for this is the fact that in the real world, there are a lot of quantities that sort of can be modeled as similar types of events, probabilistically speaking. And so the idea is that for a lot of the types of probability questions that we're going to be addressing in real life, the way that we can go about figuring out what is the probability mass function here is going to be first in identifying sort of what pattern does this experiment follow? And then from there, we're going to immediately know what is the probabilistic behavior of this. And the tool that we're going to use for this is what I will refer to as the named distributions. And so these are going to be several distributions that we're going to look at that are going to have a special name. And as soon as you know that a random variable takes on a particular pattern, you're going to know exactly what its probability mass function is, exactly what its expectation is, exactly what its variance is. And so in today's lecture, we're going to see a whole bunch of these. We're going to practice identifying them. What I would say is that we're going to see a whole lot of different equations here because we're going to see a lot of probability mass functions and a lot of expectations and a lot of variances. Importantly, you will never need to have these memorized for this class, right? So we'll always be given you the different formulas here. And so really what I would prefer you to focus on today is figuring out when is each of these going to be appropriate, and then making sure that you can tie this back to everything that we've been talking about in this class up until now, right? Because these probability mass functions, these expectations, these variances are all going to behave in exactly the same way as any of the probability mass functions or expectations or variances that we've been dealing with up until now. The only difference is that these are ones that arise over and over and over again, and so they're worth sort of pulling apart and treating as a special case. So with that, we'll pop on over to the notes here, and we'll start talking about an example that we've actually already seen several times, and it sort of will motivate this idea. Right? And so one of the things that we've been looking at a whole lot is the equally likely probability model. And so if we suppose that every value between two integers, say a and b, is going to be equally likely, we've already seen how to model this as a random variable, right? And so we can think about what is the probability mass function of this random variable here. And we've seen that in the equally likely case, the probability mass function is always 1 divided by the number of events in the sample space. And that's going to be the relevant probability for each event in the sample space, right? And so if you have a plus 1, all the way up to b, then the total number of events here is going to equal b minus a plus 1. Right, and so take a little bit of time to sort of convince yourself that this is true, right? But if we think about, for instance, a die having 1, 2, up to 6, right? Then in this case, we're going to have b is 6 A is 1, we know there are 6 possible outcomes. And so if we plug in 6 minus 1 is 5, plus 1 is the 6. And so we get sort of the right outcome here. And so what we can say is that the probability mass function of this random variable is going to be 1 over b minus a plus 1 for x in the set a plus 1 up to b. And it's going to be 0 otherwise. Right? And we've seen this before several times throughout. But the thing that's really sort of interesting to note about this is it doesn't matter what we're actually modeling here, right? It doesn't matter if we're thinking about a die. It doesn't matter if we're thinking about drawing cards out of a deck. It doesn't matter if we're thinking about pulling items out of an urn. It doesn't matter if we're thinking about selecting random people out of a crowd. It doesn't matter if we're drawing raffle tickets, right? All of these are going to be in this exact same scenario where we're picking a random number between two values where every option is equally likely. And every single one of those cases is going to be treated probabilistically in exactly the same way. So if you know how to deal with probabilities corresponding to dice, then you know how to deal with probabilities corresponding to random draws or random sampling or any of these other scenarios that are all going to follow this probability model that we're working with. Right? Now, because we can write down the probability mass function here, we can also write down explicitly what is the expected value, right? And so we can write this out as the summation over all possible values for x. So that's going to go from a up till b. And we're going to take x times by the probability of x, right? This is our definition of the expected value. So this is going to be x from a to b of x times by 1 over a minus, or b minus a plus 1. Apologies, b minus a plus 1, right? This term right here doesn't depend on x, so we can pull it out front of the summation, right? And so we can write this as 1 over b minus a plus 1 times by the sum from x equals a to b of x, right? And if we're wanting to sum up all of the values between a and b, then there's actually going to be a sort of common formula to do this. And it's not required that you know this formula, but it's sort of useful to realize, and it comes up somewhat often. And so if you sum up all of the values between x equals a and b, what you're going to find is that you get a result of 1 over 2 a plus b times by b minus a plus 1. Okay, and so if we plug this in here, right, we'll get 1 over b minus a plus 1, and we times that by 1 over 2 times by a plus b times by b minus a plus 1. Right, we can cancel this out, we can cancel that out, and so we're left with the expected value of x is equal to a plus b over 2. And this is a really useful result. So for instance, one of the things that we've worked out is that the variant, or the expected value of a die roll, for instance, if you're rolling a 6-sided die, is going to be 3.5, right? And we could figure this out by realizing that it follows this probability model. And then we take a as 1, we take b as 6, right? So a plus b is 7 divided by 2 is 3.5. Right? And so immediately, just by recognizing that a die roll follows this model, then what we have is the expected value sort of directly from that, right? And so this leads us to our first named probability distribution, and this is going to be what we will call the discrete uniform probability distribution, right? So it's the discrete uniform. And essentially what we're going to say is that a random variable x will follow the discrete uniform distribution if it takes any integer value between a and b with equal probability, right? So any situation where we have equally likely outcomes that can be referenced as the sequential integers, right? So the numbers 1 through 6 on a die, tickets 1,000 through 10,000 in a raffle, whatever the case may be. If each of those is equally likely, and we just have sequential integers, then we say that it's going to be a discrete uniform distribution. And in particular, the thing to note here is that this discrete uniform distribution is controlled by A and B, right? And so if you're rolling a 6-sided die, A is 1, B is 6. If you're rolling a 20-sided die, A is going to be 1 still, B is going to be 20, right? And so A and B here are what we are going to call the parameters of the distribution. The idea is that there's going to be sort of an infinite number of possible discrete uniform, right? Any sequence of integers is going to form one. However, each of them are going to sort of behave in a similar way. And so what we'll say is that the two parameters of the discrete uniform are going to be A, which is the minimum possible value, and we're going to also have B, which is the maximum possible value, right? And so if you know what's the minimum value that that this random variable can take on, and you know what's the maximum value that this random variable can take on, then you know sort of the full behavior of this random variable. Every discrete uniform is going to have the same probability mass function, and specifically we're going to say that the probability mass function is going to be 1 over b minus a plus 1 for x in a plus 1, up to b. Right? And it's going to be 0 otherwise. We worked this out above, right? And we can write down the mean. We already saw this. The expected value of x is going to be a plus b over 2. And we also know the variance, and you could work this out for yourself if you so choose, but you don't have to. But it's going to be b minus a plus 1 squared minus 1 all over 12. Right? And so what we can do here is, as soon as you know a random variable is going to take on any of the values between two integers with equal probability, we know its probability mass function, we know that it is an expected value of a plus b over 2, and we know that it has this variance. Now, one of the things that I'll sort of note as we go through this, right, because we're about to see a whole bunch of other distributions like this, there's some notation here. So we would say that x is discrete uniform, right, where discrete uniform is the name of the distribution, right? And so in this case, the distribution of x is the discrete uniform distribution. We might also write something like x follows a discrete uniform distribution, but we want to specify which discrete uniform distribution, and so we'll say a, b here, right? So for instance, if x is a die roll, then we might say x is discrete uniform 1, 6. Right, and so this is sort of our shorthand for meaning x follows a discrete uniform distribution. Okay? And so the discrete uniform is not the most practical distribution in the entire world, right? But it is one that we already have sort of learned about, and so we can hopefully connect this idea. But we can start to see some more useful distributions, and so for most of the rest of the class, we're going to be introducing some more of these. But so let's go on to the next one. And the next one is what we will call the Bernoulli distribution, right? Named after a guy named Bernoulli. And the idea with the Bernoulli distribution is that it's actually also quite straightforward. So a random variable x is Bernoulli if it can take on exactly two values. So any random variable that takes on exactly two values is called Bernoulli. Now, almost always we say that x has to be in 0, 1, right? But the idea is that 0 and 1 can just be labels, right? So you might also see success, failure, right? So x is success or failure, right? And success and failure are going to depend on the exact situation. Normally, we're going to call a success a 1 and a failure a 0, right? So what might we think about here? Well, for instance, a coin flip, right? A coin flip can take on exactly two values. It's either heads or tails. Maybe we call heads a success, tails a failure. So that's exactly two different possibilities here, right? You might also think about something like a plane landing safely, right? A plane is either going to land safely or it's not. And so there's exactly two possible outcomes there. And so that's going to be a success or a failure. You could think about, say, a genetic mutation occurring in some sort of, at some point along a genetic code, right? That's either going to be, the mutation is either going to be present or it's not. Success, failure, right? And so all of these are going to be what we would call Bernoulli random variables, right? The one parameter that we're going to require for a Bernoulli random variable is a parameter that we will call p, and this parameter is the probability of success. So how likely is it that x equals 1, right? So in other words, the probability that x equals 1 is going to equal p. Okay. And so if you're flipping a coin, p is going to be 1/2. If you're, seeing does a plane land safely, p is going to be, 99.999 and sort of so forth there. Now, the probability mass function, we can sort of write this out in two ways. The one way is to just note that it's going to be a probability of p for x equals 1, and it's going to be 1 minus p for x equals 0, and it'll be 0 otherwise. You might also see this written out as p to the power of x, 1 minus p to the power of 1 minus x, and this will be for x in 0, 1. And so these are going to be exactly the same thing, right? Because if you plug in a 1 here, you get p, and if you plug in a 0 there, then you get 1 minus p. We can write down the mean and the variance, right? So the expected value of x is going to be equal p, and the variance of x is going to be equal to p times 1 minus p. So Bernoulli random variables are easy enough to determine because anytime that there's only two possible outcomes, it's going to be Bernoulli. But what we actually want to do with Bernoullis is use them to construct more useful random variables for us, right? So we'll go through another few distributions here that are all based on the Bernoulli, and we'll sort of go through these ones quickly. The first one that's based on the Bernoulli is the binomial distribution, right? So it's the binomial distribution. This is going to be one of the most commonly used distributions for us. And a random variable is said to be binomial if it counts the number of successes in n Bernoulli experiments, right? So the idea here is that if you run a Bernoulli trial, right? So you conduct a random variable that is Bernoulli distributed, and you do this n times in a row, and then you count up how many times were you successful. That's going to follow a binomial distribution. So if you flip a coin 100 times in a row and you count how many heads are there going to be, right? Or if you, look at 1,000 flights and you see how many of them are going to be running on time, for instance, right? So it's counting up how many successes in some fixed number of trials. In this case, we're going to have two parameters. We're going to have n and p. P is going to be directly from the Bernoulli, so this is the probability of success. And n is going to be the number of trials. Now, something that's critically important here is that we need each trial to be independent, right? And so in particular, if you're flipping a coin, it doesn't matter if you've, flipped the coin 10 times already, right? Each trial there is going to be independent, and we need each trial to have constant probability of success. Right, and so you can't be sort of changing out which coin you're flipping here, right? So P has to stay constant across all of the different experiments you're running, and there can't be any influence between these different experiments. If either of those two things is violated, then you wouldn't have a binomial distribution, right? So those are sort of critical assumptions for the binomial. If you know that a random variable is binomially distributed, then you're going to run into having a probability mass function that is given by n choose x, p to the power of x, 1 minus p to the power of n minus x. And in this case, x is going to be from 0 all the way up to n, right? And so we need sort of this combination out front, but then it looks a lot like sort of the Bernoulli distribution there. And then we can also write down the expected value of x is going to be n times p, and the variance of x is going to be n times p times 1 minus p. And you could actually work these out based on our results about the summation of random variables from last class. Okay, and so far we have the discrete uniform, which is when you have equally likely outcomes over integers. We have Bernoulli, which is whenever you have exactly 2 outcomes. And we have binomial, which is when you count up how many successes were there in some fixed number of trials, right? The next distribution we're going to look at still is based on the Bernoulli experiments. It's called the geometric distribution. And the idea with the geometric is that instead of performing an experiment a fixed number of times, we're going to perform an experiment until we see a success, right? So a random variable x is geometric if it counts the number of trials in Bernoulli experiments until one success. So here, instead of knowing how many experiments we're going to perform in advance, we're thinking about there being sort of as many trials as it takes until we see a success. Right? This, like the other ones based on the Bernoulli, is going to be characterized by a parameter p here, and p is going to be still the probability of success, right? And so what we're thinking about here is, you're going to flip a coin as many times as it takes until you see a head, for instance. Or you're going to keep looking at plane flights until one of them is running on time, right? Or you're thinking about a professional baseball player, and you're going to count how many times does it take for them to go up to have an at-bat until they actually hit a home run, for instance, right? And so we need a sort of a constant probability of success. We still need independence of the different trials, but if you're in that situation, the geometric counts how many trials to get a success. The binomial counts how many successes in a fixed number of trials. We can write down the probability mass function here, and it's going to be equal to p times by 1 minus p to the power of x minus 1. And in this case, x is going to run from 1, 2, 3 upwards, right? There's sort of no upper bound on the possible value for x. It might take you sort of an infinite number of trials to work this out. Now, if you want the expected value of x, this is going to be equal to 1 over p, and the variance of x is going to be 1 minus p over p squared. Okay, we actually worked out the expected value and the variance of this in a past lecture without knowing this, but we sort of started from this probability mass function here, right? So you can go back and look at that now. But now, if you know that what you're doing is you're counting up how many trials does it take until you see a success, you know immediately this is the probability mass function, and this is the expected value, right? So if you're flipping a coin, you know that you're going to expect to see 1 over 1/2, which is 2 tosses until you see your first head, right? And so that's going to give you sort of an easy way to work these things out. Now, the negative binomial is very, very similar to the geometric, right? And so we'll just sort of jump right into it. A random variable x is negative binomial if it counts the number of trials on Bernoulli experiments until r successes. So like the geometric, we're going to keep performing the experiment until we see successes. However, in the negative binomials case, we need to have this second parameter here, r, which is the number of successes. And so if you take r to be equal to 1, then the negative binomial and the geometric are exactly the same thing. But if you take r to be anything else, then it's going to be a different distribution. So you might want to know how many times is it going to take me to toss a coin until I see 10 heads, for instance. So the number of successes to stop, and p is going to be the probability of success, right? And again, we're assuming that all of these are independent with constant probability of success. If a random variable is negative binomial, then it's going to have probability mass function given by x minus 1, choose r minus 1, p to the power of r, 1 minus p to the power of x minus r, where x is going to start this time at r. It's going to take at least r trials for you to see r successes, and then r plus 1, r plus 2, and so on. Again, there's no sort of upper bound to it. The expected value and the variance are going to be quite similar to the geometric, right? So we're going to have r over p for the expected value, and for the variance, we're going to have r times 1 minus p over p squared. And so again, if you take r equals 1 here, then you get exactly back to the geometric. However, this is going to be more general, right? And so you could think, again, you need to get, say, 10 heads, right? Then r is going to be 10. P is still 1/2. So then you'd have 10 divided by 1/2 for 20 flips of the coin is what you would expect until you've seen 10 different heads. So to recap where we're at so far, right? We've seen the discrete uniform, we've seen the binomial, and the Bernoulli, we've seen the geometric and the negative binomial. Now we're going to look at another 2 different distributions here, right? And I know it's sort of a lot to take in, but then as soon as we've looked at those, we're going to go through a whole bunch of examples where we try to understand what distribution they're going to follow, right? So hopefully you can follow along as we introduce these last 2 different distributions here, and then sort of get some practice getting them all applied. So the next one that we want to look at is hypergeometric. And a hypergeometric is going to be different from all the other ones that we've looked at so far, because the hypergeometric is not going to be based on Bernoulli random trials. Instead, the hypergeometric is going to be counting up successes still, but where sampling is going to be happening where the probability of success is not constant. And so in particular, what we're thinking about is if you have a finite population, so you're thinking about, for instance, a deck of cards, right? And you're sampling without replacement, right? So every time you draw out a card from your deck of cards, the probabilities are going to be changing, right? And so a random variable x is hypergeometric if it counts the number of successes when sampling without replacement from a finite population. So, for instance, we might be thinking about how many spades do we expect to get if we draw 10 cards, right? So there, we have 52 cards. It's going to be a finite population. We're drawing 10 of them, right? And we're going to be sampling without replacement. If we were sampling with replacement, so you draw a card, you put it back in, you shuffle the deck up, and you draw another one, then we're going to be performing 10 trials with constant probability of success, and so it becomes binomial. With the hypergeometric, we're thinking about never putting that card back in, and so the probabilities are changing. It's not binomial. It's going to be hypergeometric instead. And so in the hypergeometric distribution, we actually need 3 different parameters here. We need what we'll call big N, we need M, and we need a small n, right? And so what are these different parameters here? Well, big N is the total population size. And so, for instance, in the deck of cards example, big N is going to be 52, for instance. M is going to be the count of successes, right? So how many of the total population are considered to be successes. So in this case, if we're thinking about spades as being successes, then there would be 13. And then little n is going to be the number sampled, right? And so if you're taking, say, 10 cards out of it, then you would get 10 here, okay? So there's a total sample size of capital N. M of those items are going to be successes. Little n is going to be the number that we sample. And our idea is we want to know how many of the items sampled are going to be successes, right? Anytime that we're sampling without replacement, right? And so you could think about here, say, sampling out of a population, right? If you want to know, for instance, how many people in a population, something the size of a town, for instance, have a particular genetic condition, then you could, sample out of that town and sort of see there where, again, you have some fixed population size, some portion of them are going to have that genetic condition. You're going to be taking a sample of a certain size, for instance. For a hypergeometric random variable, we're going to have a probability mass function here, and it's going to be given by capital N minus M, choose little n minus x, right? And so this is going to be the number of ways that we can choose the non-successful items. Then we're going to have M choose x, right, which is how many ways can you pick x items from m successes. And then in total, this is going to be divided by capital N choose lowercase n. And in particular, we're going to have x is going to be in a range here, and it's going to be starting from the from the larger of 0 and n minus m plus n, right? And it's going to go up to the minimum of n and m, right? So what are we thinking about this range on x here? Well, the upper bound here, all we're saying is that if you draw out n items from this population here, then at most you could have either n total successes or m total successes if there are fewer than n items, right? So if you think about drawing cards out of a deck here, right? If you're going to draw 5 of them, well, then you could have 5 spades because there are 13 spades in the deck. But if you're going to draw 20 cards, right, at most you could have 13 spades, right? You couldn't get 20 spades because there are only 13 there, right? And so we go to the minimum there. In terms of the lower bound right here, right? Well, of course, you can never have less than 0 items here, right? But if you think about what this n minus m plus n is, right? Well, n minus m is going to be the total number of items that don't have success on them, right? But we need to add on to this the number that we're drawing, right? So what are we thinking about here? Well, if we were to draw, say, 50 cards out of the deck, right? How many of those could end up being spades? Well, what we know is that at most, 2 of the cards are not going to be spades, right? If you're still left with the 2 spades in the deck, because there's only 2 cards going to be left in the deck after we draw all of these out, right? And so if we plug this in, n is going to be 52 minus 13 plus 50 here, right? And so then 52 minus 13 is 39. So I have a fairly silly mistake here, so my apologies for this. This should say m minus n plus n, okay? So m minus n is going to be the total number of items that are not successes sort of in the negative form, and then adding back n is how many of those we're going to ultimately end up speaking out, right? And so if we had it the other way, you could have seen that we would have gotten like 89 or something. But if we plug it in this way, and again, apologies for the confusion here, if we take 13 minus 52 plus n is 50, right? So then in this case, if we actually work through the math here, we're going to find that this is 11, right? And so the idea is that the smallest number of spades that you could have if you draw 50 cards is going to be 11, because at most 2 of them aren't going to be spades, right? And so you have to have at least 11 of them. So again, apologies for the confusion there, but you're going to have at least either 0 or m minus n plus n, right? And why do we take the maximum here? Well, for most cases, if you think about, say, only drawing 5 cards, right? So if you draw 5 cards, then we're going to have 13 minus 52 plus 5. This is going to be a number that's less than 0. But of course, you can never get more or less than 0 spades, and so you need to take the maximum there. Hopefully that made a little bit of sense. Again, sit down with the card example and look at it otherwise. But that's going to be the range we're looking at. And then sort of once we know that, once we've seen the distribution here, we're going to find the expected value of x is going to be n times by capital M divided by lowercase m, divided by capital N, lowercase n times by m divided by n. And then the variance of x is going to be given by, and this is a slightly longer expression here, so it's n times by m over n times by n minus m divided by n times by n minus n over n minus 1. Okay. And I would encourage you to read through the course notes a little bit and take a look and see how this is actually related to the binomial distribution. It's actually quite a lot similar there. But so that's all talked about a lot in the course notes. But just know that in terms of when do these arise, well, they arise whenever we're sampling without replacement. Okay. The last distribution that we want to look at, and again, we'll take a look at some examples of all of this as soon as we've seen this last distribution, is what's known as the Poisson distribution, right? And so the Poisson distribution is going to be even more different than the hypergeometric. And the idea is that a Poisson distribution, or a random variable x, is going to have a Poisson distribution if it counts the number of occurrences of events in a set time or space or similar. Okay, and so what are we thinking about here? Well, if you're thinking about, for instance, how many individuals are going to arrive at an emergency room over a 24-hour period, right? None of the distributions we've looked at so far are really going to capture that idea there. And so counting up that number is going to follow this Poisson distribution. You could also think about, say, sitting outside at an intersection and counting the number of cars that go by. Or you could think about something like if you're a manufacturer, you're manufacturing some rope, for instance, how many defects are there going to be in 100 meters of the rope, right? So all of these, you're counting up how many occurrences of events are there going to be in some fixed amount of space, right? So either that space is an area or that space is some time period, right? And you just want to count up how many times is the event of interest going to occur. The Poisson distribution has one parameter, it's lambda, and this is the rate of events occurring, right? And so if, for instance, you know that, say, 10 people arrive at the hospital per hour, then lambda would be 10, right? Assuming you're looking at a single hour there. Now, once you know that something follows a Poisson distribution, it's going to have the probability mass function given by e to the power of negative lambda, lambda to the power of x divided by x factorial. And this is going to be defined for all positive integers, right? So we can see 0 occurrences, we could see 1 occurrence, 2 occurrence, and so forth, right? Now, the Poisson distribution is interesting because the expected value is going to be lambda, right? Which makes sense. This is the average rate of occurrence. If 10 people arrive per hour, then we expect to see 10 people in an hour. But the variance is also going to equal lambda. And so the Poisson has this interesting trait whereby the expected value and the variance is exactly the same. Okay. And those are all of the name distributions we want to look at. Again, I know that this was a lot of information to sort of cover here. And so what I want to do now is actually just start looking at a whole bunch of examples and trying to identify which is which in terms of distributions here, right? And so hopefully this will start to solidify things a little bit. But I'll remind you that in this class, you don't need to actually memorize your different formulas here. And so I would encourage you to perhaps pause this video now and try to see if you can start to match some of these to the different distributions that we've talked about. But I'm going to start going through them, and at the start, we'll sort of take a little bit of time justifying them, and then as we go on, we'll probably spend less and less time on each of these examples. So the first example here is the number of spades that show up in poker hands of a fixed size, right? Now, we don't know what the size of the poker hand is, but what we do know is that when you deal out a hand, you're dealing from a deck of 52 cards, and you're going to be dealing out some number of them, and you're not going to be replacing them, right? And so what we know here is that we're sampling without replacement. Anytime you're sampling without replacement, then you think hypergeometric, right? And with the hypergeometric here, what we would be thinking about is big N is going to be 52, big M is going to be 13, and little n is going to be the hand size, right? And this is sampling without replacement. That's how we know it's hypergeometric. Okay. In part B, we're thinking about the availability of some particular book at some particular library, right? When you look at this, what you should think is, well, there's two options here. It's either available or it's not. Anytime that there's only two options, then immediately we know that this is going to be Bernoulli, right? And if it's Bernoulli, then the parameter we're looking at is P. And in this case, that's going to be, say, the probability the book is available. Right? And so here, the reason that we know that is because it's a binomial experiment. There's only two possible outcomes. It's either there or it's not. Okay. And option C, the number of defects in 200 yards of yarn. Well, here what we're thinking about is we want to count up some number of events, right? In this case, it's going to be defects. And we have some fixed amount of time or space, in this case, 200 yards of our product here. And so what we know is that this is going to be Poisson. It's always Poisson when we're counting up the number of occurrences in a fixed time or space. And here, lambda is going to be the average number of defects, right? If X is going to be the result of a die roll from a D-sided die, well, what we know about dice is that they're always going to be equally likely outcomes, right? Equally likely outcomes in the parlance of named distributions always corresponds to discrete uniform, right? And the discrete uniform here, if we're thinking about it being D-sided, well then what we'll do is we'll take A is equal to 1 and B is going to be equal to D, right? So if it's a 6-sided die, 1 to 6, right? So it's discrete uniform because we have equally likely outcomes. Option E here, the number of individuals who respond to flyers that were handed out, there were 50 flyers handed out in total, advertising some show. Okay, so here we can treat each individual as being an individual experiment, right? Each person is either going to respond or they're not. There's a fixed number of trials. And so what we know is that we're counting up how many successes we have in a fixed number of trials. Number of successes in a fixed number of trials is always binomial, right? So this is going to be binomial. N is going to be 50. Right? Because there's 50 flyers handed out, and P is going to be the probability of response of any individual. Okay. F is the number of people that arrive in an emergency room over the course of the next hour. Well, we actually, introduced this as an example when we were talking about it, but we're counting up the number of events over the period of time. So anytime we're counting up events over time or space, we're thinking Poisson. And so that's going to be having a lambda, which is the rate of arrivals of people. the number of people you have to meet until you find someone born on your birthday, right? So what are we thinking about here? Well, if we think that each person's birthdays are roughly independent of each other, there's going to be a 1 in 365 or a 1 in 366 chance of them being born on your birthday, right? And so what we're doing is we're counting up how many times do we have to meet people until we get a success, right? How many trials does it take until there's a success, where success is defined as the number of someone having your same birthday. Anytime we're counting up trials until a success, this is going to be a geometric, right? And so geometric here is going to have a parameter of p, which is 1 in, say, 365, assuming that each birthday is equally likely. Now, we want to know the number of houses that we would need to visit in order to sell 10 chocolate bars for a fundraiser, right? Again, we're counting up how many trials do we have to do, right? Visiting different houses is going to be a trial here, but instead of stopping after 1 success, we're going to be stopping after 10 successes, right? Anytime you're stopping after a success number greater than 1, we're not thinking geometric, we're thinking negative binomial. Right, so this is going to be negative binomial, and here we're going to take r is going to be 10, because that's how many times we need to be successful before we stop, and p is going to be the probability of a sale. All right, we have several more examples here, and instead of identifying each of the parameters this time, we'll just go through and find the different distributions, right? So Z is going to represent the score that a student earns on a 20-question multiple choice, given that they're guessing on every single question, right? So here, each time they get a question right, that's a success. We want to know how many successes do they have in a fixed number of trials. Anytime you're counting up successes in a fixed number of trials, it's always going to be binomial, right? The number of visitors that are showing up to a website on any given day, right? We want to count up the number of events. In this case, the number of events is a visitor coming to a website in some period of time on a given day, right? Counting up events in a particular time or space, always going to be Poisson. How many stores do we need to visit until we find a particular product in stock, right? Well, we're repeatedly visiting stores, so repeatedly performing trials. We're going to stop when we get to a success, right? So we're counting up how many times do we need to perform a trial until we get to a success, always going to be geometric, right? Now, if you needed to find multiple of these in stock, for instance, then maybe it's negative binomial, right? And so you can sort of think about how we could expand these out. How many black swans are seen on a visit to a swan sanctuary? So here we have to sort of figure out what is exactly meant by this. But what you might imagine is that there's going to be some fixed number of swans at this sanctuary, right? And what we're going to do is visit each of these swans until we see we're going to see, some number of them, and we want to count up how many of them are going to be black swans. And so what we're going to be doing is, if we're assuming that we could tell each swan apart, then we're sampling from these swans without replacement. Anytime you're sampling without replacement, we're thinking hypergeometric. So hypergeometric, and in this case, we would think about capital N being the total number of swans, lowercase n being the number of swans we're going to see, and m being the total number of black swans at the sanctuary. Got a few more to go through here. Is the plane running on time or not, right? 2 options exactly. It either is or it isn't. Success, failure, 1, 0. Anytime there's only 2 options, we immediately think Bernoulli. Okay. The number of defective parts in a batch produced by a manufacturing process when 8% of all parts are defective. This is going to be counting up how many successes we have, where here a success is there being a defective part, in some fixed number of trials, where the number of trials is how many parts are in this batch, right? Constant probability of success. And so what we're thinking about, counting number of successes, fixed number of trials, we always think binomial. 3 more to go. Number of rolls until we see 6 sixes on a 6-sided die, right? So here we're going to keep rolling the die until we get to our 6th six. So we'll stop after we have 6 successes, right? Anytime you're going to be stopping after some fixed number of successes other than 1, we always think of that as being negative binomial. The number of songs in a shuffled library that come up during a fixed listening session, which are our favorites, right? So what we're thinking about here is we have some library of songs, right? There's some number of them there. Some number of those are going to be our favorite songs. And what we want to know is how many, if we listen to, say, 100 songs, are going to be our favorites. We're sampling from this library without replacement. Anytime we're sampling without replacement, we get to hypergeometric. And the final example here is the number of users that clicked on a banner ad on a website out of the next 1,000 visitors if 5% of all users do this. Well, here what we're thinking about is there's some fixed number of trials. Each one either clicks or doesn't. We want to count up how many people do. So we have binomial. So I would encourage you to go through these, and I would encourage you to go through all of the examples that are provided in the course notes as well. Right after you start getting used to identifying the distributions here, it sort of will become second nature for you. And the really nice part is that once you identify that a random variable has a particular distribution, you know its probability mass function, you know its expected value, and then we can take all of the tools that we've been working with so far and start talking about the different probabilities associated with this. And so that's sort of everything that we wanted to cover today. I know that it was probably a lot. I encourage you to go through these lessons. And when we get back from reading week, we'll touch on this a little bit more and we'll see sort of where we're going to go from this point forward in the term. Hopefully that was clear. Again, please reach out to me if you have any questions whatsoever. And I hope you all have a wonderful break.